A robot arm is in mid-surgery, the network drops for 40 milliseconds. That's not a glitch, that's a malpractice lawsuit waiting to happen. This is why 5G built for hospitals, factories, and power grids is engineered completely differently than the 5G in your pocket. And by the end of this video, you will understand the exact design trick that keeps these networks from ever going down. Right now, telecom operators worldwide are racing to deploy networks that can't afford a single second of downtime. We're talking about self-driving cars making split-second decisions, remote surgery robots controlled from hundreds of miles away, and power grids that keep entire cities running. If any of these networks fail even briefly, the consequences aren't inconvenient, they're catastrophic. Let's start with what failure looks like for normal everyday 5G. Your video buffers for a few seconds. A call drops and you have to redial. It's annoying, sure, but nobody gets hurt and nothing breaks. This is the baseline most of us experience every day, and it's built with a certain amount of tolerance for error because the stakes are simply low. Now let's raise the stakes. In a smart factory, 5G controls robotic arms on the assembly line in real time. If the network drops for even a second, a robot arm can misalign mid-weld. The entire production line stops. Depending on the factory, that's tens of thousands of dollars lost per minute, plus the cost of scrap materials and delayed shipments. This is where 5G networks start needing real redundancy and not just good enough connectivity. Now the highest stakes of all, remote surgery, autonomous vehicle collision avoidance, power grid control signals. These systems can't just tolerate occasional failure. Regulators now mandate that they fail effectively 0 times per year. That standard is called 5 nines or 99.99% uptime. To put that in perspective, 5 nines means less than 5 minutes of downtime allowed across an entire year. So how do engineers actually build a network that's allowed to fail 0 times a year? There's one specific design trick telecom companies use that most consumer networks don't even have, and I'm going to show you exactly how it works in a minute. But first, you need to understand why redundancy alone isn't enough to get you there. You might think the answer is simple, just add a backup connection, but basic redundancy has a fatal flaw. If both connections rely on the same physical tower, the same power source, or the same core network, one single point of failure can take down both at once. Real reliability requires something smarter than just having a spare. The real solution is called dual connectivity failover. Instead of one connection with a backup, the device maintains two fully independent, simultaneously active connections, often from different towers, different frequency bands, sometimes even different carriers. If one connection degrades or drops, the second one is already live and takes over in milliseconds before you'd ever notice a gap. This is the design trick that separates mission-critical 5G from everything else. On top of dual connectivity, operators layer in AI-powered monitoring that watches network conditions in real time and predicts failures before they happen, thus adjusting power, rerouting traffic, or flagging a degrading tower before it fully drops. It sounds like a complete solution, but AI monitoring has one blind spot most people miss, and it's the reason human engineers are still very much in the loop. The blind spot is simple. AI models are trained on past failure patterns. They struggle to predict a completely new type of failure they've never seen before. That's why every mission-critical network still has human engineers monitoring systems around the clock, ready to step in when something unprecedented happens. This exact combination of dual connectivity, AI prediction, and human oversight is already shaping how 6G networks are being designed from the ground up. So to recap, mission-critical 5G is built differently in 3 key ways. Dual connectivity failover eliminates single points of failure. 5 nines uptime standards set a nearly impossible bar for reliability. And AI plus human monitoring catches what either one alone would miss. Together, that's what allows a robot to perform surgery, a car to avoid a collision, and a power grid to stay lit without ever going down. Next time, I'll show you what happens when even 5 nines isn't enough, and the emerging technologies engineers are testing to push past it toward true zero downtime networks. Subscribe so you don't miss it.